this video, we will build on our previous skills of graphing polynomials together with our understanding of long division of polynomials to work on how to find all of the zeros of a polynomial. So let's begin. We want to begin with reminding ourselves of the factor theorem. Remember that for a polynomial, if x minus c is a factor, then it must be that c is a zero, meaning that if you were to replace every x in the equation with that value c, you would get 0 as your output for y. Similarly, if you have a 0, c, you have a factor x minus c. They go both ways. That's called an if and only if, the double arrow. They imply each other. So to fill in our first blank here in our slide, we say if we have at least one blank of a function, we can use long division to find another, and this is known as our division algorithm. What do we mean by that? Well, what we're saying here is if someone were to just hand you one factor of a polynomial, it turns out that you could use that factor and long division and other shortcuts to find another factor, okay? So the answer here for the blank is at least one factor. Now, why is that? You could think about just numbers, for example. Forget about polynomials. Let's go back to something we're more comfortable with. If someone were to come up to you and say, I have a number, maybe one of your students in elementary school that you have, or a friend who's small or younger, and they say, I have a number, 112, and I need to find some factors of it. If you wanted to give them a clue, besides teaching them some cool tricks like divisibility rules, you could say, here is a number, and they could then use that number to check if you're telling the truth, and then if you are, to find another factor. What do I mean by that is, if you were to tell them, hey, I think 3 is a factor, or I think 4 is a factor, they could then do long division, right? And if in the end of their long division, they end up getting a remainder of 0, then you were telling them the truth, and that was in fact a factor. But in the process, if you did tell them one that was truly a factor, whatever number they got as their answer to their long division is called the quotient, and that quotient would be another factor. So by someone giving you a factor, you could use division to find another factor. That's what we're saying here. So if the remainder is 0, that's the key. If the remainder is 0, then we have truly found a factor. Excuse me. So let's begin with that scenario, but for polynomials. Suppose we have a polynomial f of x equaling 12x to the second power plus 7x minus 12. Now, if someone were to come up to you and say, I think that 4x minus 3 in parentheses is a factor, you could say thank you very much, and then you could check if they're actually telling you the truth. All right? So how would you do that? Good old-fashioned long division. You might think, oh no, I hated that. It's going to get worse, so brace yourselves. We're going to go through this algorithm one more time, step by step. Are there shortcuts? Yes, but sometimes the shortcuts won't apply. So we do need to know how to do this long division to check. So let's take a look. What we did in American long division, I know other countries do things differently, so feel free to do it the way you were taught. I don't want to confuse you overly. But in America, we put what we're dividing into under the house, right? And then we put what we're dividing in outside. And on top, we'll put our quotient, our answer. The first step in that algorithm, if you remember, was to look at the leading terms and ask yourself, 4x times what would give me 12x to the second power? Yeah, that's right, 3x. So where do I put that? Well, traditionally on top of its like term, so on top of the 7x, right? Then once you've done that, I'll switch colors here, see if we can see it here. How about white? Once we've done that, we would multiply by whatever's in front. So if I multiply that 3x times the 4x, we'll get 12x squared, won't we? But we can't just multiply it to one of the terms, we have to multiply it to the entire thing in front. So term by term gets distributed. Well, 3x times negative 3 is negative 9x. Again, we would write that in the next available spot under its like term. Well, the next step in that algorithm was to subtract, right? Subtraction. But to subtract a polynomial really means to subtract every term of the polynomial, meaning that we have to change our signs. One thing that students like to say to remind themselves of this step is draw the line, change every sign. Draw the line, change every sign. I usually like to circle my sign change to make sure I see it, right? At this point, I notice that 12x squareds cancel because they had the same sign. And then I repeat my algorithm after I combine like terms. So let's do that. 7x is now being added to 9x, which results in positive, 16x. Notice if you had the sign change not there, you would have had the wrong answer there, right? You would have had 7 minus 9, which would have been negative 2. So make a little note there if you made that mistake or if you felt inclined to make that mistake, because as humans, we tend to repeat our mistakes. And I would rather, honestly, don't take this as not doing homework, but I would rather my students not do any homework than to do things incorrectly over and over again. Because if we continue to practice the same mistakes, we continue to hardwire those processes in our heads. So make sure that you put a little note there. If you were thinking of making that mistake, make a little note and rewire those connections in your brain. Always draw the line, change every single sign. Okay, now that we have that 16x, let's bring down our next term, which is negative 12. Great. Well, at this point, we repeat our algorithm. We say the leading term only, 4x, goes into the leading term 16x how many times? Yes, that is correct, positive 4. So I put that above its like term. Then I repeat the algorithm one more time. We continue until we get a remainder, either of 0 or of something else. So when I now multiply by whatever's in front, I'll get 4 times 4x, which is 16x. And I'll get 4 times negative 3, which is negative 12. Now we're in luck this time. Your friend wasn't lying. This is going to be a factor. And how do I know that? Because when I draw my line and change my signs, in other words, when I subtract, I get a negative 16x, which will cancel with positive 16x, and I get a positive 12, which will cancel with my negative 12. So in this situation, we have a remainder, I'll put REM for remainder, of 0. Whenever our remainder is 0, that meant this truly was a factor, because otherwise we'd have something else as a remainder. So in the process of confirming that this was in fact a factor, we actually stumbled upon another factor, which again, if you remember the factor theorem from on top here of the slide, at the top of the slide, as soon as I find a factor, I really have a 0. And if that's a real 0, I really have an x-intercept. So this is really going to help us in our graphing process. So what we've just found is that another factor here is actually this answer on top, our quotient, which was 3x plus 4. So 3x plus 4 is our other factor. Now you might have already known that because you were taught in your previous classes how to factor a quadratic trinomial like this, maybe by the AC method or trial and error. So if you had come up with that yourself, great job, pat yourself on the back, you remember how to factor, I'm proud of you, that's great. But what we're trying to do is show you with this nicer, easier example again, how long division is a way to check whether or not something is a factor. And again, what is the rule? If the remainder is 0, then it is a factor. Beyond that, we could now rewrite our function. So instead of the expanded form that they handed us, we can now write it in factored form. What would that look like? Well, for factored form here, we would now have our function, you got to name every function, f of x. The output function f of x would equal 4x minus 3 as one factor, and that's multiplied by the other factor, 3x plus 4. Now, you should always check yourself when you're starting out, when you're learning how to do something, right? Did I actually do this correctly? And the way you can check there is by simply foiling, right? 4x times 3x, 4x times 4, negative 3 times 3x, negative 3 times 4, combine like terms. You should get right back to your expanded form version. If not, you don't have the right factors, do you? Why do I bring this up? Because now we have the x-intercepts, don't we? By setting each factor equal to 0, in our previous videos, we talked about how this allowed us to get our x-intercepts on our graph, and even to know what happens at those x-intercepts. If I were to set 4x minus 3 equal to 0, letting y equal 0, wouldn't I get that x equals 3 over 4? Or 0.75, if you actually were to click on Desmos, the link there, you'll see it's at 3/4 or 0.75. And another x-intercept, when you let 3x plus 4 equal 0, moving the 4 to the other side, it becomes a negative 4, and dividing by 3, we would have negative 4 over 3 when we let that factor equal 0. So at negative 1 1/3. So those are my two x-intercepts. I also know my end behavior. Remember from last video, we talked about the degree and the sign of the leading coefficient. Here the degree is 2, which is even, and here the leading coefficient is a 12, which is positive. With that information, we know that at the ends we're going in the same direction and they're both going positive. We also now know that the x-intercepts are going to be at 3/4 and -4/3, meaning that we are going to actually cross the x-axis somewhere. So if I were doing a little sketch, I could do that. Let's get a little sketch here. Kind of ugly, but you get the idea, I hope. We are in fact going to have two x-intercepts here, one at -4/3 and the other at +3/4. So something like that's happening in our graph. We are crossing because their multiplicities, again, were odd. So if you're not remembering that, check out the last video where we talked about how to graph polynomial functions using end behavior and zeros. Okay, with that information now in hand, knowing the factor theorem and knowing about long division, we can now check if someone gives you a potential factor, whether or not it is a factor, and if it is, we can find another factor in the process. So let's take a look at our next example, shall we? Example 1. It tells me to use long division to check if the second polynomial is really a factor of the first polynomial. So again, I set up my long division here. There are shortcuts that we'll talk about in a few moments, but let's go through it the long way. At this step, I would really encourage those of you who were kind of tracking with me in the first slide to pause this video and try it yourself, and then come back and see whether or not you have every part right or if there's some areas where we're prone to error. Okay, all right, let's do it. So what I notice here is that I have x plus 1, and I'm trying to see if it goes in evenly to the function f of x. First things first, we notice hopefully that there is in fact a missing term here. The x cubed term is not present. Whenever we have a missing term, when you're doing long division in your setup, you can either leave a gap, which I hope you noticed I left a massive gap here between the 4th degree and the 2nd degree term. Or, in my opinion, the best way to do it is to write a placeholder term. There are 0 copies of x cubed, so I would just write plus 0 x cubed. Now, you might be thinking, that seems silly. I don't want to write 0 x cubed. Fine. Just please watch yourself carefully, because when we don't have a placeholder, or at least a space separating the like terms from the unlike terms, it is very tempting as humans to combine things that cannot be combined legally. So please be careful. All right, let's continue the process, the algorithm here. We look at our first leading term and our next leading term, and we ask ourselves, x times what would give me 3x to the 4th power? That's right, it would be 3x to the 3rd power, and we'll put that on top of its like term. Next up, remember what the process was? We would multiply by whatever was in front. So we got 3x cubed times x. Well, that's 3x to the 4th power. And then 3x cubed times 1, that's 3x to the 3rd power. Remember the next step? Subtract. In other words, draw the line and change every sign. Negative 3x to the 4th, and now it's negative 3x to the 3rd. Combining like terms, let's see what happens. The 3x to the 4th should cancel if we built it correctly. Watch your signs carefully. 0 and -3. Again, it could have had a blank spot there, and we would just bring negative 3x cubed down, along with our next term, negative 6x to the 2nd power. Okay, next up, we repeat our algorithm. X times what gives me negative 3x to the 3rd power? That's right. It would be 3x to the 2nd, but negative. Negative 3x to the 2nd power. We repeat the algorithm with multiplication, and negative 3x squared gets multiplied by x to give me negative 3x to the 3rd power. Negative 3x squared gets multiplied by the 1, and that's just negative 3x squared. When I draw my line and change my sign, subtraction, this becomes a positive 3x cubed and a positive 3x squared. When I combine my terms, like terms, the x cubed terms will cancel, but be careful here with your x squared terms. What do we get? Negative 6 plus 3 is negative 3. So we get negative 3 copies of x squared. Make sure you really understand how to add and subtract like terms. Sometimes students will make errors here and they'll try to change the exponent. But remember, if you change the x squareds into, let's say, an x to the fourth, you've really gone from saying something like -6 apples and +3 apples to now saying I have -3 apple oranges. That doesn't make any sense. You need to maintain the same type of situation that you have, the same type of term, and that is an x squared term. You have -6 copies plus 3 copies, so we have -3 copies of that type. Okay, bring down your next term and let's repeat the algorithm. So we ask ourselves again, self, x times what gives me -3x squared? That's right, -3x. And we multiply it by everything in front as our next step. -3x times x is -3x squared, which is what we wanted. -3x times 1 is -3x. Now be careful really here because we can easily make an arithmetic error if we're not really paying attention. When I change my sign subtracting this step, I get +3x, x squared, which does cancel with its like term above it. But notice here I have to change into a +3x as well, which means that even if you were tempted to cancel, we can't, can we? Because we have a positive with a positive, which results in a +6x. If you think you might have made a mistake there, make a little note. Got to have that sign to distribute the change in both places. Continuing the process, we'd bring down our next term. We're almost done, I promise. I know this was a tedious one. We would say again, our leading terms, compare them. X times what gives me 6x? Yes, +6. And then we would be able to multiply that by everything in front. And let's see what we get. 6 times x is 6x. 6 times 1 is 6. And drawing the line and changing the sign, we'd get -6x and -6. Combining those like terms very carefully. The 6x terms do cancel since they have opposite signs, but the -7 and the -6 do produce a remainder of -13. I don't know if you can see that. I'll try to write it a little higher for you, sorry. So we do get a remainder of -13. If that remainder is not 0, that's telling us something. That's right, it's telling us that x plus 1 does not go in evenly into this function, into this polynomial. In other words, if -13 is not a, sorry, not -13, if x plus 1 is not a factor, if x plus 1 is not a factor, which is what this is telling us, the factor theorem would then tell us that -1 is not a real 0 or an x-intercept. So in the process of looking for x-intercepts, which we'll be doing much more in future lessons, one of the ways we do that is using division, long division, to see whether or not we have a factor. And then if we know we do or we don't, then we also know whether we do or we do not have a real 0. Okay. Again, I feel free. I recommend checking out those Desmos graphs that I've already pre-programmed into your slides so that you can take a look and see what was the x-intercept. Is there an x-intercept? And in this graph, you would be able to tell that it is not at -1. Okay, let's try another example here. Let's head over to our next one. In the next slide, what we'd like to do is give you an alternative way of checking whether or not you have a factor. So the long division way will always work, right? Because we can use it for any type of factor we're checking, whether it's a small factor like we just did, x plus 1, or a really large factor like x squared plus 5x minus 7. Okay. Long division always works. But if we have a linear factor like the one we just did, x plus 1, or in the one in this example, it's going to be x plus 2. If that's the situation, we have another way we could do this, and it's a shortcut. It's called synthetic division. Synthetic means not real, right? So synthetic. So it's not the real long division, but it is a way of doing it that still gets the job done in a nice short way. So let's take a look. It only works if we're trying to check if x minus c is a factor. So notice that has to be linear, that we're checking a linear factor, and it has to have a leading coefficient which is equal to 1. So if we had like 2x plus 4, that wouldn't work for synthetic division, but it would work if it was just x plus 4. Okay. So what are we doing here? Well, the first thing we want to do, we'll do an example and hopefully that'll help make it come more alive to you. Suppose we're checking if x plus 2 is a factor of f of x equaling the polynomial in expanded form 2x to the third power minus 3x to the second power minus x plus 2. So in this situation, we could do long division. We've just tried it that way. In fact, if you really want to hone in your long division skills, feel free to go ahead and do that one in long division as well, okay? But we're going to show you a different way right now. Using synthetic division, what we're really going to do is, instead of checking is this a factor, we're going to use the factor theorem to check is negative 2 a 0. Why negative 2? Because if x plus 2 is a factor, then when I equal it equal to 0, shouldn't I get x equal negative 2? I do, the factor theorem. So what we actually check is whether or not negative 2 is a 0. So with synthetic division, you make a little box, if you will, and you stick your potential 0 that you're checking inside that box. Notice to the right of it, we stick our coefficients of our polynomial that we're trying to divide into in descending order, so from the highest power down to the lowest power, being very careful that if we've had any terms skipped, like if I didn't have an x squared term, you'd have to put a 0 there, a placeholder, if you will. So notice in this case, there are no skipped terms, right? We go down from a power of 3 to a power of 2 to a power of 1 to a power of 0 with our constant. But in your homework, there will be times where we skip a term, and you'll have to remember that means I have a placeholder of 0 there, okay? So I put 2, negative 3, negative 1, and 2 in order. I leave a little bit of a space, and then I draw a line. Now, step 1, after you do this initial setup, is to simply draw a line and bring down that first number. So we bring down our 2, if you will. Step 2 in this algorithm is to multiply. It's kind of reminding me of long division. You might see something familiar here. 2 times negative 2 is negative 4. We're going to plop that number in the next available spot. The second step in the algorithm that we keep repeating is addition. So we have multiplication and addition. So we do this addition of negative 3 and negative 4, and that produces a negative 7. Now, if you have no idea what these numbers are, that's okay. I haven't told you yet, but you might have a clue, and that's great if you do. So let's take a look at what happens next. We repeat the algorithm. We'll multiply that negative 7 by whatever's in the box, which was negative 2. And a negative 7 times a negative 2 we know is positive 14. Repeating the next step of the algorithm, addition, we would get negative 1 plus 14. That's right, 13. Next step of our algorithm, multiplication. 13 times negative 2 is negative 26. Now, this is where we have the really important information. If we've done it correctly, if we haven't made any arithmetic errors, when we add down this last term, we add it each time, right? When we add down this last term, these last terms together rather, 2 and negative 26 gives me negative 24. Whatever you get as your final sum in the addition steps will be your remainder. So we have a remainder here of negative 24. Now you might think, well, that's not 0. This isn't very helpful. And you're right. This one turns out to be the case where x plus 2 is not a factor, or negative 2 is not a 0. But here's what is interesting about synthetic division and why it is a really helpful tool instead of long division in certain cases to be able to check for factors. If the remainder had been 0, so if this had been 0, this right here, these numbers at the bottom, these would be the coefficients of your quotient for the next factor. So right now the quotient, if you were just doing the long division, what's your answer, what's your remainder? The quotient would actually be 2, x to 1 power lower because you divided by a linear factor, so x to the second, minus 7x, and your constant would be positive 13. So if you're just interested in long division, which we're really not, we have a purpose for this. But if you were in a lower level math class and they just said find the quotient, find the remainder using synthetic division, there's your quotient, there's your remainder. For us though, we're going to be more higher level in our thinking. We're going to be applying this to graphs very soon. So for us, the real thing that we've discovered using this long division is because the remainder is non-zero, it's not equal to 0, that means that negative 2 is not, it is not a 0 of our function. So negative 2 is not a 0 of our function. Similarly, by the factor theorem, it goes both ways, x plus 2 is not a factor. Okay, it's not a factor of our function. So by using synthetic division in a much cleaner and quicker way, I was able to determine whether or not I had a 0, which meant whether or not I had a factor. But there is another way. I don't want you to think there's always just long division or synthetic. Technically, if you are a 0, if negative 2 was in fact a 0 of this polynomial, then when I replace x with that number, so if I were to actually do f of negative 2 and plug that in for x in each of these locations, carefully, it should have equaled 0, shouldn't it? But in reality, it will end up equaling whatever this remainder was. In this case, it would end up equaling negative 24. And you can check that on your own, right? So if it was truly a 0, when you plug in that number, the potential 0, it should give you a 0 for your y value. So that is a shorter way, I will tell you that. If you had plugged it, pre-programmed it into a scientific or to a graphing calculator, 2 times parentheses something to the third power, minus 3 times parentheses something to the second power, minus parentheses something plus 2, and then replace each of those somethings in parentheses with the number you're checking, that's a quick way. That's probably the quickest to know whether or not you truly have a 0. But the reason I will prefer synthetic division every time is that if I get a 0 using the synthetic division process, if I get a remainder of 0 here, then I found the next factor. So that's why I would recommend this. Okay, let's practice again in another example. Feel free to pause me at any point to try on your own. This one's just like it. It says, can you use synthetic division to check if the second polynomial is in fact a factor of the first? So we could do long division, which would be very tedious here, but this is a candidate for synthetic division because we have a factor potentially of x minus a number. So if we're checking if x minus 1/3 is a factor, aren't we really checking if this is a 0? And by this I mean 1/3. Because the factor theorem said that if x minus c is a factor of your polynomial, then c is a 0. And again, that's because you're solving for x when you set it equal to 0. Let's repeat the algorithm, shall we? Putting 1/3 in the box, notice what we did here. We have our leading coefficient of 3, followed by 8, followed by 1, the coefficient of x, followed by 1, our constant. And if there had been any skipped terms, we would have used zeros for those places. We begin the algorithm by bringing the 3 down, remember that? Next up, the next step was multiplication. Now we do have fractions here, and most Americans have been trained to hate fractions. If you're going to be successful in math as a STEM major, you have to overcome that fear. So let's dig in and start to love fractions because they're actually quite fun. Let's take a look at 3 times 1/3. Well, isn't that really 3 over 3, which is 1? It is. Then I can add down. 8 plus 1 is 9, that's right. So I have given you some quite nice numbers so far. Hopefully you're enjoying them. 9 gets multiplied now by 1/3. That's 1/3 times 9. I can write it out if some of you need it. 1/3 times 9. But 3 goes into 9, so that's really 3, isn't it? So we have that as our next number, which we can add to 1. So far life has been pretty good in this problem. 1 plus 3 is 4. Okay, repeating my algorithm one more time, we can multiply 4 times 1/3. If you do that, don't you get 4/3? So 4/3 would be our next number there. Now you might already see the answer, right? I'm not going to be able to get a remainder of 0 here. But if you were asked to get the quotient and the remainder, you could finish off the problem by adding up those last 2 terms. 4/3 plus 1, well, 1 is really 3 over 3, isn't it? Getting a common denominator. That's really 1, if you will. So we have here 7 over 3 as our remainder. And here again, they only asked us the question, is the second polynomial a factor of the first? Because this is not equal to 0, we would say, no, this is not a factor. And if that's not a factor, if x minus 1/3 is not a factor, that also is telling us by the factor theorem, it goes both ways. That's also telling me that excuse me, 1/3 is not a 0. So it goes both ways. If x minus 1/3 is not a factor, then 1/3 is not a 0. It goes both ways. All right, so we've now given you a lot of tools in your toolbox to start checking whether or not you have factors. You might already be thinking to yourself, so are they always going to give me potential factors to check? If you're thinking that, you're on the right track. The answer is no. We're right now trying to just build your confidence and give you some tools in order to check things. But in reality, moving forward in our future lessons together, we will have to be on the hunt ourselves for x-intercepts. We will have some tools to be able to try to guess, but then once we have some options that we need to check, we will apply synthetic division. So make sure you really do practice this. Math is not a spectator sport, so go ahead and practice this, become an expert at synthetic and long division before I see you next time. All right.